Hello and welcome to the Exploit Development 106 lecture on advanced shellcode and payloads and return-oriented programming techniques. My name is Dr. Owen Redwood, and the guest lecturer today is my colleague and friend Dr. Devin Cook. This lecture is part of the Offensive Computer Security 2.0 open courseware hosted at hackallthethings.com. Today's new lecture will cover the following sections. 1. Tips and techniques for gadget hunting. 2. The analysis and design of advanced payloads and advanced shellcode techniques. And then 3. A demo given by the guest lecturer of ROP gadget hunting, gadget catalog building, and building ROP chains and using them in exploits. So to begin, we've briefly covered ROP so far, and the gadget sparsity problem you should be familiar with. If you have enough gadgets, your payload capabilities approach Turing completeness. Let's cover how to find gadgets for both ROP and shellcode. In general, I find the following tools very useful for this. Object Dump, ReadElf, or PE parsing tools, grep, for debugger, the GEF or PEDA add-ons developed by the community for the GNU debugger, GDB, are exceptionally useful and just great tools. ROP Gadget is a tool developed by Jonathan Salwin, who is the author of Programming from the Ground Up. It's a fantastic tool and resource. Mona.py definitely deserves mention. It's been developed by the fantastic Corlin team. And PwnTools and PwnLib are Python libraries that you can pip install that are worth looking at, especially for their packing convenience. In this lecture, we're going to break gadgets down into two types: classical gadgets and then special gadgets, which often completely defeat ASLR and partial RelRo. There are some gadgets that completely defeat even full RelRo. So for classical gadgets, we have general ROP, JOP, and COP gadgets. There's a more recent technique that came out in 2013 called signal-based ROP, which attacks the signal frame for signal handlers of Linux or Unix systems. And then there's gadgets that you can find in binaries and libraries that have not been that have been compiled without NX support. And these actually, in practice, in the real world, get imported by Java and Flash, especially in a browser. If you see a malicious page with an empty Flash player, it is importing those libraries so you can ROP to them very easily. Dropbox also notoriously did this in the past and was a great source for gadgets for attackers. Special gadgets include fixed VMA addresses that you can jump to or point to and rely on even in full ASLR and full RelRo to always arrive at the destination function. These are things that are hard coded kind of into the binary design or the kernel, and it will vary depending on OS, but typically most systems have these things, and they're considered more so on the secret side of the OS development. For a topic that we've already covered, fixed jump slots is also what is specifically in the global offset table, the GOT. And we've discussed and demonstrated exploiting a vulnerability by overriding a pointer in the GOT table and getting that pointer to trigger shellcode. There are other special gadgets worth mentioning for embedded systems and multi-lib architectures that are more specialized and revolve around exploiting fixed direct memory addressed regions or fixed DMA'd regions. In the end, with the right combination of gadgets, you can pretty much do anything to a system. So you should be, before getting any further into this lecture, be familiar with the previous lecture's coverage of return chaining theory and be able to, on paper, go through how the stack works across multiple functions and understand this process. The following is a general methodology for ROP that is 6 steps and is pretty reliable. The first step for exploiting the vulnerability with ROP is 1. Acquire a pointer to anywhere inside of libc. This is often accomplished through info leaks. However, if you can find and use special gadgets on the target, such as jump slots, these are very useful here for acquiring a pointer to libc. Step 2. Use an offset-based approach to determine the location of either mmap or mprotect within libc. 3. Find push EAX, then ret, or push RAX, then ret gadget, and you will need this for the very end. 4. If the target allows you to create via mmap a memory segment that can be marked readable, writable, and executable, then create a readable, writable, executable memory segment and copy the payload into it using mmap. Otherwise, if mmap does not allow you to create a RWX segment, create a read-write memory segment, copy the payload to it, and then use the mprotect gadget to change that segment from RW to RX. Step 6. Finally, utilize the push EAX gadget to execute the shellcode. When mprotect returns, or when mmap returns from steps 5 or 4 respectively, EAX or RAX will be populated with a pointer to your new memory segment with the payload. That is why the final step is to utilize a push EAX ret gadget. A lot of people hype up jump-oriented programming and call-oriented programming. It's very similar to ROP. And if you can ROP, you can do JOP and COP and everything else oriented programming. Some examples of JOP and COP gadgets are pop EBX, jump EBX, pop EBX, call EBX. In GCC compiled binaries, often EAX and ECX are overwritten during a normal stack smash. So often a direct jump or call EAX or ECX gadget may be quickly exploitable to jump straight to a payload, given that it has been put in memory and is marked executable. RAX and RCX may be affected similarly on 64-bit systems. Your next step is to look for gadgets that will allow for JOP or COP to mmap or mprotect, and then follow the previous methodology. Again, it's that simple. If you're looking for advanced training on JOP and COP, you just got it. So signals-based ROP comes from a fantastic paper it was in 2015, Playing with Signals, an overview on SIG return-oriented programming. So the way SROP works is that on the left we have what a signal handler expects to be constructed before jumping to the kernel's, before entering the kernel's signal handler. This is supposed to be constructed by user space. The kernel 100% trusts that it is valid. However, this trust is misplaced, and this signal frame is completely abusable. On the left, we have a valid signal frame, and it starts here at FP state, or a pointer to it, and it's being set to null. CR2 is here, and then it lines up like this. The proof of concept is highlighted in red, and it is it is walked through on this POC link. You can feel free to go through it. It's a very good read. It does, however, rely on a fixed VMA that's a special gadget, which we will cover shortly. So this has limited application. That fixed VMA, when GR2 packs are enabled, often will lock down that VMA, so it limits the use of this. This should almost be put into special gadget use, but I digress. So CS is overwritten. Old RIP and RSP, so old EIP, old ESP, old AX and DX are overwritten. Same with RSI and RDI. And then the rest of it is constructed normally. And what matters is a syscall gadget and a previous RIP, and then finally the shellcode and a pointer to the shellcode, say in somewhere in the BSS or memory. It requires you to construct all of this to exploit it, so it is very complicated. It's not going to be required for this course or the exam, and it would be considered more of an advanced topic outside the scope of this class at the moment. Finally, the last category for classical gadgets are simply binaries and libraries that are compiled without NX support. In other words, the binary allows every memory space to be readable, writable, and executable, which makes it a great place to put your shellcode and find gadgets and everything else. You can check how bad your system is about this with the checksec tool from trapkit.de. The easiest way to do it is to run it with --proc--all. It will check all running processes. I have provided a sample from a stock Xubuntu, so Xubuntu, install from 64-bit 1504, and the number of binaries and libraries that do not have NX support is atrocious. So, on Unix systems, if it's marked with no Pi support, that means it is not a position-independent executable. Therefore, it relies on fixed positions to execute properly. Therefore, ASLR cannot be applied because it cannot safely or reliably rearrange memory segments due to that reliance on fixed addresses. Partial RelRo and full RelRo we have covered somewhat. Partial RelRo further rearranges some memory segments that ASLR does not address, and full RelRo attempts to rearrange the rest. A notable oversight in partial RelRo is that it does not address GOT rearrangement, and therefore the GOT and the global offset table, that's what the GOT stands for, and all of the jump slots within it will stay at a fixed address in every ELF binary, which means exploiting vulnerabilities for partial RelRo systems, even with ASLR on, is trivial, because you can override the GOT all day long. I don't know why the community has accepted this crap. Stock distribution should not be shipping with so many binaries compiled and distributed without Pi support and without full RelRo support. It's not a performance issue, I guarantee you. So, it was discussed in a previous lecture on web application exploitation that something like 95% of all websites found in 2014 that had that were hosting browser 0 days and end days and browser malware were utilizing just a simple empty Flash player to get these easy gadgets, because the Flash player included the DLL or shared object does not have Pi support and does not have ASLR support. So it always exists at a fixed address, and therefore it is very reliable for attackers to use in their exploit and payload. This is not to be confused with exploiting Flash vulnerabilities. Now, to recap, to enable kernel mode ASLR, you would set procsys kernel randomized VA space to 1 or 2, preferably 2 for full. 1 is partial, so it's very ineffective. The following compile time mitigations work for your GCC: fstack protect all, fpie, w1, relro, and the -m mitigate -rop cflag is new. It works for 32-bit x86 systems, somewhat experimental, so I'm not sure about the stability yet. If you have a Unix system, you should absolutely look into applying grsec, pax, and kern heap patches for the Linux kernel to harden your system. Hack All the Things offers a professional training, a one-day workshop on building from source, patching with all of these patches, and maintaining hardened, ultra-hardened Linux systems. So now for the special gadgets. For the first category, we're going to cover some Unix fixed VMAs. These are always static and fixed. For ELF32 binaries, the address of 804.8000 will always contain a pointer to the base pointer of the currently executing binary, 100% of the time, even with ASLR on and full relro. The address of 804.80BC contains a 4-byte VMA pointer also to the currently executing binary's dynamic section. Similarly, for ELF64 binaries, the address of 4.00000 will always contain a pointer to the base pointer of the currently executing binary, 100% of the time. The address of 4.0.0.130 also contains a 4-byte VMA pointer that points to the currently executing binary's dynamic section. The great thing about these gadgets is that they work when there's full ASLR and full relro. They always work. grsec and pax do have some settings in the kernel hardening options to alert and spit out alert messages in the logs that'll pop up and say demessage, but they won't do anything to mitigate this factor, this category of gadgets. And I've just shared 2 gadgets for 32-bit and 2 for 64-bit that do the same thing. There are many more special gadgets that well, it would just be unfair if I gave them all away. The next category, jump slots. These are what occupy the global offset table. When partial relro is on, this segment is readable, writable, and executable. It's located at a fixed address and is filled in on demand during runtime by the program interpreter. Again, we've covered this before in the exploitation of it. However, when full relro is engaged, these are filled in, set to readable and executable only, but they are still occupying fixed locations. So you can rely on them for info leaks if you can direct, say, a format string vuln to read that address. The 32-bit entry for GOTs and 32-bit binaries do not contain nulls, which is very convenient for info leaks. Because when you try to get an info leak to print out a pointer that contains null bytes, you will get less than a full width pointer. So you may have some truncation, you may lose some significant bytes. Now there are fixed VMAs on multi-lib systems. I just call them multi-lib VMAs. I'm pretty sure these only apply for binaries that are compiled with a compiler that has multi-lib extensions. And so a really good example, there's multiple ones, but I'm only going to give away this one, is FFFF6000007. And that is always a fixed gadget to syscall. It is very much like SROP. It's actually, this one is specifically utilized in the SROP proof of concept. This one, actually, GR2nd packs will explicitly block any userland code trying to return to this gadget, and it will scream alerts and demessage logs, but it won't mitigate the other ones that I shared. So this is all really cool stuff. I love ROP, and there's sometimes movies and media gets it right. This is a screenshot from the ROP chain and malware or exploit code that was built in the movie Elysium to reboot that space station, and for the good guys to go and win the day. Not to spoil it too much. If you haven't seen it, go see it. That doesn't spoil enough. But you'll see here that's Python code, ROP, pack, and some gadgets, and then comments saying what the gadgets are. And this is some Russian subtitle. But let's discuss, now that we've covered ROP, which is a pillar for modern binary exploitation, advanced payload development, and dive into advanced shellcode. This GIF is from Ghost in the Shell. It's a good anime series. So, in this section, we're going to cover the anatomy of shell codes. So we're going to cover loaders, encoders, stubs, payloads, tools, modules. We're going to cover some tips for defenders for hunting shellcode. That's for malware reverse engineering and digital forensics incident response. And then finally, we'll touch on some analysis and design of advanced shellcode, and dive into building dynamic shellcode. So, there are many phases of exploit development, and there are many phases of developing a payload for a given target once you have an exploit. Often payloads are developed once and used multiple times, so therefore it's really advantageous to have advanced payloads that can work on multiple operating systems and systems. But before we get too far into that, we need to cover the fundamentals. In shellcode and payload terminology, a loader is a tool that's primarily used on the attacker's local system during their testing and development phase, but it can also be part of more modular payloads and modular malware. Effectively, they are simple procedures or assembly instructions that get a pointer to the shellcode, mmap some memory segment, set its permissions if necessary, move the shellcode to that segment, and then maybe tie up a few other things, set arguments, and then ret to the shellcode or jump to it in some fashion. There are dynamic loaders, which we will cover in a little bit. Encoders are used to change bad bytes and problematic bytes and areas of the payload that may flag in IDS systems that have known signatures and other heuristics into a different byte. It does this by systematically iterating over the entire payload or parts of the payload, changing the bytes by a fixed scheme that is reversible so it can't be decoded. These are used to evade signatures, IDS systems, and to bypass any character filters that may be present in the attack vector. Often, most people are exposed to encoders through Metasploit, Shikata Ganai's. I think that's their most famous and popular encoder option for their modules. Stubs allow more modular payload design with small code snippets that can be used interchangeably for various tasks. So anything that's sufficiently small and abstract is typically called a snub. It may be used for just simply setting up arguments in a way this desirable and have no other side effect. Now, dynamic code in a payload allows for extra features from shared libraries and DLLs to be used, as well as advanced forms of obfuscation and detection or evading detection. So to drill down more into stubs, they're just usually small code snippets that are less than 50 bytes that are used during payload initialization and staging. They may go as far as importing specific functionality or doing red pill based techniques. So detecting virtual machines is specifically what red pills refer to. But they may do other forms of fingerprinting, such as architecture detection, operating system detection, register investigation, such as getPC. They may involve unpackers or decoders, and they may offer, finally, more advanced red pill stubs include anti-debugging techniques, anti-detection techniques, and sandbox techniques, as we discussed, the virtual machine detection red pill stubs. Now, for defenders, there's multiple tips that I want to cover for hunting shellcode. The first one is defenders typically do runtime analysis on just the contents of RAM in both data and executable mark segments. They may even go as far as to inspect kernel interrupts and system calls from within the kernel. They may also monitor the functionality of LD runtime resolve, which is sometimes a trampoline to DL fixup, provided by LD Linux for a normal application to make library shared library calls. 2. Many systems will alert on any process that tries to execute system calls or interrupts if that process does not have such things in their .text segments, or when a process attempts to use the following to import a function that's not listed in its import table: LD runtime resolve, DL fixup, DL open, DL close, or DL sim. Defenders should look for instances of alerts in the logs for these occurrences. This should be one of the very first things you do when hunting shellcode. 3. Often, using functions such as DLOpen and DLSim require the use of plain text strings, which can be easily spotted by the malware analyst. Often, taking a binary memdump carved out with volatility or some other tool and running strings on it will dump all the strings. Getting full pass to libraries or pass to or function names and just the full string is something that should be cross-referenced against the IAT table for the given binary. If it has strings for functions that are not in the IAT, you got a problem. That's a sign of shellcode. Any skilled analyst would be able to reverse engineer the payload once they've spotted a string in shellcode, which is a problem for almost all traditional shellcode. They typically rely on string arguments for bin.sh or some other argument. 4. There are many common shellcode signatures. The bytes 0f05 is a 64-bit opcode for a syscall. The bytes CD80 is a 32-bit systems opcode for int80, and so on. There are many opcodes that are specific to traditional shellcode design. int80 and syscall are probably the two biggest ones. Now, these are 4 really great fundamental tips that malware analysts should be doing all day. Again, to reiterate, make sure you do runtime analysis in the contents of RAM for both data and executable mark segments. Possibly hook the functionality of LD runtime resolve, DL fixup, which is often a trampoline used to make shared library calls. Look for any alerts in the logs for processes trying to execute system calls or alerts that aren't in the processes .text segment. 3, make sure to look for strings, and once you find the strings, you found possibly the shellcode if they seem suspicious enough. And 4, look for the common shellcode signatures, especially for the opcodes. Now, and strings like bin.sh. Now, given all these tactics that defenders can use to play the devil's advocate, there are things that an attacker can do to avoid detection by the aforementioned techniques we just covered. Specifically, if attackers in their shellcode constructed a linker that allows them to construct a dynamic self-linking payload that imports functions from shared objects and libraries without any assistance from the operating system, this discards the need for interrupts and system calls entirely. And so malware analysts looking for these signatures would not find them. Similarly, you can implement function hashing, which we'll cover specifically in a few slides, to avoid using function names in the payload itself. Instead, the function hashing technique is very similar to the Windows land malware technique of calling functions by their ordinal. And here we utilize a one-way hash to find strings in a target library, hash them, and compare them to the no good hash. So you're only using hashes and doing direct checks to determine whether or not you've iterated on the target function. So this solves the problem that we just discussed of shellcode often needing strings that are dead giveaways in malware analysis. So we're going to cover these two topics, function hashing, a linker, and all under the purpose of Tor's dynamic shellcode, so that malware analysts can be aware of these situations and can adapt to react to them. So to build a payload linker in shellcode, you first need to understand the calling convention for the platform, its executables, and shared library file formats. This is also referred to as knowing the platform's abstract binary interface, or ABI. Then, the next requirement is being able to recognize and use artifacts found in the memory of the process that you're currently exploiting to construct or import functionality as needed. Now again, remember the special VMAs that we covered. Those give pointers to the base pointer of the text segment as well as the dynamic segment, which is where all of your DLLs and shared object libraries will live. So given these resources, you can import the functionality of the existing process and all of its shared objects to your shellcode payload arbitrarily. And so moving forward, the main components of dynamic code include but are not limited to stubs for fingerprinting the platform, specifically in this case for identifying the library memory space, and that will differ in implementation and parsing for Windows land libraries such as ntdll.dll and Unix land ldlinux.so's shared object. Another component that's important is hashing function, which is some form of one-way function hash that takes a string and computes a hash. It doesn't have to be anything fancy. It can be completely custom, but it has to be deterministic. 3, a file format parser such as ELF32 or 64 and or PE32 and 64. Finally, dynamic shellcode requires export table searching algorithms to look for shared libraries, specifically parsing the global offset table, the GOT, or the export address table, the EAT. The resolver should take the address of a shared library, iterate through the memory space, finding function strings, or whatever signatures you may instead use to identify functions, and compute the one-way hash of the string or identifier, and then compare it to what you are looking for. If you've found a match, then you have found a pointer to the function, and you can either return that pointer to use later, or you can utilize it immediately to invoke the function directly. So let's cover function hashing, because we just talked about it a lot. This is very similar again to calling functions by ordinals for Windows malware, and the methodology is simply to calculate the hash of the target function before deploying the exploit and payload, then iterate through the library memory space, that memory segment, looking for the function hash. You may be able to start at a fixed location where your identifiers would normally occupy, and then compute the one-way hash iteratively. Once you find the match, you then invoke the function with the hash. And the rest is pretty straightforward. By doing this systematically, you can avoid detection by most modern shellcode detection techniques. So we're going to borrow an example method for function hashing that's several steps long from nets.ec wiki page on dynamic shellcode. It's a actually very good wiki for forensics and incident response and defenders to just browse through in general. There's a lot of stuff that really is eye-opening in terms of what shellcode and malware can do. So if you have free time and you are in incident response or malware analysis, it's really worth browsing that wiki and bookmarking it. But I digress. So we're going to cover 6 steps of this function hashing prototype. It simply expects 2 prerequisites: that RDX is zeroed out, and a pointer to a given string is in RSI. It then iterates, or it simply just takes this pointer and makes a one-way 32-bit hash of the string and places the hash of the function into RSI. That's all this function does. And then we're going to show, after we complete this function, how you can iterate over a process function table or a library function table with this function hashing process, and find your target function. So first, you want to write a stub that simply preserves the registers that you need. So we have calc hash, and it's just commented out. This is a to-do. And then we have the preserve regs func, which is just going to push RAX and RDX to the stack to preserve them. Now, since the RDX register is zeroed, it is used as a 0 register for the rest of the algorithm. And you can do this by pushing RDX and then immediately popping whatever register you want to 0. So here we're zeroing RAX because we pushed 0, and now we're popping it, overriding RAX. Next, you want to also clear the directional flag. This is because LOD_ST is used during the hashing process, and the state of the directional flag is going to be unknown up to this point. It may be anything arbitrarily set by the vulnerable application in the current state. So CLD is a command for that. Then, to make the one-way 32-bit hash, we use LOD_SB, which in x86 will load a byte, word, or double word from SI and store it into AL, AX, or EAX. Here we are doing LOD_SB, which will only load a byte, and it's going to store it in AL. And the source for it is pointed to by ESI. This next instruction may throw off most, but it's quite common in hashing functions. We're going to rotate to the left by 12 bytes the value in EDX. For the first iteration, EDX is 0. But then we take EAX and we add it to EDX, and it gets stored in EDX. Now EDX is no longer 0, unless the very first byte that was returned by LOD-SB was a null byte. Otherwise, it would have some data from the string. And so it checks to see whether or not AL is a null byte by doing test AL, AL. And if it's not 0, it jumps back up here. If it is 0, it means that AL has a null byte, and it would continue going on. So then for the second iteration, it would retrieve another byte, and it would iterate, go to the next byte pointing to by ESI, and then you do the roll, which is rotate left of EDX by 12 bytes, and then you add again the byte that you've loaded into EDX, and you keep going. You keep rotating and adding and rotating and adding and rotating and adding until you've got a null byte. And then at the end of this function, EDX contains your function hash. Now you want to push EDX so that you can move it into RSI via pop. Alternatively, if it's not an opcode that contains null bytes, you could just do move RDX RSI. But I digress. Now the last step is to restore the functions that we preserved on the stack, RDX and RAX, and it will return with RSI containing the function hash. Now, for the fun part. In practice, this allows you to parse the dynamic process header memory space to locate any functions export table and utilize that to ROP to target functions. The fun thing is no strings are required at all in the shellcode payload. All you need is 32-bit hashes for the given function names. You can call functions of multiple shared objects as long as you can point to them all, and those special VMAs that are fixed that we've mentioned before will help you with that. So, remember how I said that in partial RelRo and full RelRo, the GOT occurs at a fixed space. Let's use object dump to look at it so you can picture exactly what's going on. Here we have an Ubuntu VM, and in the terminal here we're going to play with object dump, and we're going to use the R flag, which looks at the dynamic symbol table, and say for bin ls. It's going to show us the address, some attributes, and then the function string names. Now this is actually more information than included actually in the GOT. In the GOT, it is simply a 2-column table where each row is for a single function. The one column points to an array of strings, and the second column points to an array of function pointers. Now, they both use the same index in the GOT table to index into their respective lists. And so that makes it incredibly compact and simple. When you use object dump, it simply parses this out, retrieves the information, and prints it out for you instead of just giving you the raw pointers. But for the function pointer, it gives you the raw pointers here on the left. And this is the given offset. And the value of the string is the thirdmost column. And so what we're doing in the function hashing algorithm that we just finished going over is we're loading 1 byte at a time, adding it to the EDX register, and rolling, doing the hash. And we keep going until we get a null byte. Now, what happens is if you keep track of your place in this table, you then can easily access the offset. Because once you determine that, hey, I have a match in my hash that I'm looking for, you can then easily call the function that you need to call. And if it has not been populated by the program interpreter, it will get populated on demand for you. which is nice and convenient. And so then, given the function pointer, you can ROP to that target function. And this is the core of a dynamic shellcode linker engine. Let's cover another example of this by invoking functions that we found with function hashes. So, the remainder of these slides are going to go over the proof of concept dynamic linker engine, which can invoke functions with just mere function hashes, and the previously discussed function hash algorithm. This proof of concept simply requires that a function hash is present in RBP, and that the memory segment base pointer that you're targeting, that you're trying to invoke a function in, is in RBX. Step 1. This is absolutely mandatory this time. You must preserve all of the registers that may interact with libc and all the registers that are used by the linker shellcode. And so we're just going to have this stub that pushes them all to the stack. And we're going to pop them all at the end. Step 2. You want to zero out the RDX register and place the function hash into RDI for future comparison. So you can do XOR RDX RDX and then push RBP, which is where we have the function hash as the argument, and then pop it to move it into RDI. Now, step 3. You want to move the base pointer of the desired library's memory segment to import into RBP. Push RBX, pop RBP. After step 3, we now have a pointer to the desired dynamic section in RBP. And this is a base pointer for that memory space. Now, given the base pointer, as I said with the global offset table, there are things in the ELF file format as well as the PE file format that always occur at fixed addresses. One such artifact is a pointer to the dynamic section of the given memory segment, which will always occur at the offset hex value 130. So if you simply take your segment base pointer, which is RBP, and add it to 130, you will get a pointer to that segment's dynamic section. This is some hacked together code that will accomplish this. Simply adding 130 to RBX will have null bytes. So pushing a 1 byte value and then multiplying it by 4 with the x86, this is add functionality, we can arrive at this value. You can verify that the hex value 4C multiplied by 4 will equal 130. Here we're simply pushing this onto the stack and then popping it into RAX and then using add RBX to RAX times 4 and then storing that value in RBX. Now, this now points to the dynamic section. And what we want to do in the dynamic section is parse it and try to find the function export table for this given memory segment. Typically, this table is called the dynsim table or dynamic symbol table. We want to do this by iterating through the headers of the dynamic section, which we're pointing to right now, and check for the type of dynamic section. Now, the headers are going to be simply a table, and one of the columns in the table is type. And it's pretty well known that the type for a function export table in a dynamic header table or a dynamic symbol table is 5. And so what this does is it keeps iterating one row at a time, checking for an entry in the dynsim table for a type that is 5. And once it's equal, it will continue on, and that brings us to step 6. This will allow the RBX register to be positioned at the correct program header for the dynamic symbol table's export function table. We can then use this to place the absolute address for the string table into RAX and the absolute address for the dynamic symbol table back into RBX. Now, and these will now occur at the given offsets. Step 7. You want to increment to the next table entry and move the pointer to the entry's string into RSI. This is so that we can begin hashing each entry's string and then checking it against this hash that we're looking for. So, iterating over the table to get to the next string entry is a matter of iterating by hex value 18. RDX is still 0. And by pushing RDX and popping into RSI, you are zeroing out RSI. Then, by zoring this will zor the lower half of RBX with SI, which is now zeroed out, so we'll move the lower half of RBX into SI, and then you can add RAX to RSI and store in RSI. Now, why do we do all this? RAX contains the location of the dynamic string table. This RSI contains the location, the index into the current table you're looking at. That index dictates the index into the dynamic string table, and so this is giving you a pointer directly to this row's string. Step 8. Then the calc hash label is invoked as previously defined and hashes the function. Then we check the current hash, which is step 9, and if it checks out, we have a winner. If not, we jump all the way back to check next hash, which is step 7. But in the case that we have a match, step 10 is once it is found, the function offset in the dynesim is located at given RBX is currently pointing at it, the offset of hex value 8, and it is a 4-byte pointer. So, RDX is still used as a 0 register and can be used to access the 4 bytes without nulls. You can simply just add them to RBP, the base pointer, like this. Add at the offset of 8 from RBX the value of RDX 0 times 4 and store it into RBP. And so RBP contains a pointer to our target function. After all this work, that's what we can now call. We've linked to an existing function and we can ROP with it arbitrarily. So, before we want to do that, we want to restore all the registers and return the target function location. So we want to move this value, say, further down the stack, restore all the registers, and this, moving it by 30, actually moves it to the return address, and that ret will trigger it. There are a lot of benefits of dynamic payloads. You can evade ltrace and ftrace debugging. You can evade all of the popular malware analysis techniques that I discussed. You can import functions from any shared object that currently exists within memory. It has a high level of portability for executable code that will persist across library changes and versions. And it allows for much higher level functionality implementations of shellcode. And you can easily defeat signature-based analysis. You can use any registers you like. It is free of system calls and free of interrupts. You can also add polymorphism on top of this to make recognition statically by signature-based detection nearly impossible. So, what we've covered so far is classical and special gadgets, bypassing mitigations with them, and basically the flaws in all existing exploit mitigations that we've discussed. And finally, advanced payload design and analysis. That is it for kind of the the lecture side of this video. I would now like to hand the video over to a demonstration of ROP tools and techniques presented by my friend Devin Cook.
All right, so here's the demo that I wanted to show you guys. Um, Now, this is just a really straightforward binary, like a very simple buffer overflow here, and you can see there's a vulnerable function that's called. There's a buffer with 32 bytes worth, and it just reads in unbounded using string copy. Um, and if you look down here where the call is, you can see that it's taking it from the first argument. Um, all right, uh, so what we need to do then is we need to overflow this buffer and write in our ROP chain, starting at the return address from this vulnerable function frame. And you can see this string here not used. Initially, I was going to use it to execute like an execve for binsh. And it's oftentimes it's easy if you can find a string to use within the binary. That way you don't have to build it yourself. But unfortunately, where it placed this, the address range that it placed the globals in when I compiled it, had characters in it that I needed to avoid. Now, so for things like string copy, you have to avoid null bytes. And then the issue that I was running into initially was that if you pass in an argument on the command line and you don't quote it properly, then new lines will get interpreted as terminators. So yeah, there are a bunch of different characters that you occasionally have to avoid, and there are always ways around them. Like we said, as long as you have enough gadgets, you can do anything that you need to do with return-oriented programming. So that's why it's pretty cool. So this is a decent example of how to get around that kind of stuff. But yeah, so this is just a very simple, straightforward exploit here. So let's take a look at the ROP chain that I built. Or actually, first, let me show you the gadgets. So you can use some tool like ROP-Gadget, or some custom one that you scripted up or whatever. All you need to do is you go through and you look at the bytes in the program, and you find which bytes can be interpreted as valid instructions, and the ones that you're looking for specifically are like simple instructions followed by a return usually. Also like int 80. So in Linux, this is throws an interrupt for a system call, which we have to use because we want to call execve to run a shell. um, but yeah, so you can see here, like, it's just 1, 2, or 3 instructions followed by a return. So like this instruction here writes to a certain area in memory. You've got exchange instructions, move instructions, to copy between registers. So you can pretty much do whatever you want to do as long as you have enough of these little gadgets. And we can see here that there are quite a few of them. ROP-Gadget found 52. All right, so that's great. So, and ROP-Gadget will also like attempt to print out an exploit here, and this is pretty neat. If you put in the correct padding here, so like remember our buffer was 32 bytes long, and then there's like some additional padding that goes on for alignment and whatnot. So you just need to know how far it is to get to EIP when you're writing your exploit payload. And if you put that in, then oftentimes this will work. It was not working when I played with it, and additionally, I wanted to kind of show you guys how to create your own ROP chain, do your own thing, kind of kind of deal. So um, of course now I think I realize in hindsight that the reason it wasn't working was um, due to misquoting uh, the input string when I was trying to execute it. But anyway, um, so like I said, we want to run an execve call, and we want to run like binsh. We want to get a shell out of this. Excuse me. And basically, here's the goal for an execve. So we need to set EAX to 11, which Linux specifies as the number for execve system call. And then EBX needs to contain an address pointing to the string of the binary that we want to execute. So that needs to be a null terminated binsh string. ECX needs to point to basically the arguments that the function is going to get. So this is like a null terminated array of pointers to strings of the arguments. And the only argument that we're giving it is just argument 0, or the program name, which will be an address to binsh null terminated. So basically the same value that's in EBX needs to go here. And then EDX needs to just be a 0 or a null. This has to do with the third parameter to execve, which is like an array of environment variables to set up. And then once we have all of those values set correctly, we need to make it return to an int80 instruction, which tells Linux that you want to do a system call. And then the kernel goes and looks at these values and determines what it is that you want to do. Okay, now the way I decided to do this was to basically put the binsh string within the junk for in my payload in the beginning. So this will actually go at the start of the buffer. Okay, so as the payload's copied in, this binsh string will be sitting at the beginning. Now, keep in mind that this will not be null terminated initially, which means that we need to go back and fix that. Okay, so that's the first thing that I do here. And you'll also note that I have some hard-coded addresses in here, like this one. So like I'm not using address space layout randomization just for simplicity, to show you guys how this works. Because what I want to do is I'm going to step through this in a debugger, and we can watch it and see exactly what's going on. So in order for this to work with ASLR, you'd need some kind of like address disclosure vulnerability as well, where you can figure out the correct offset for things. All right, so basically I load up the address of the binsh string, or specifically one past the binsh string, so that I can put a null byte there. Now you'll notice that I put 2 slashes at the beginning here, and the reason for that is that the address on the stack where this payload started ended in 400, so it ended in a null byte. And later on, you'll see, like down here, when I load the address of the binsh string, you can't have a null byte here, or your string copy that you're abusing is going to stop copying. So I went ahead and scooted all those over 1 byte, so that I can have an 01 instead of 00 there at the end. Okay, so let's see. So I load up the address where we want to put our null byte, and now with the gadgets that I had, it was easiest to just write a whole like a whole D word of zeros, because I mean it doesn't really matter, like as long as the byte directly after this H is a 0, a null byte, then we're fine. So let's see. So there was actually a gadget. If we go back and look at that, there is a gadget for zeroing out EAX, but I was having issues with getting that address to copy correctly. Again, I think that was just a quoting issue, but Here's a way you can get around something like that. So there's always a way to get a 0, and here is just one of those ways. So you pop in, basically this D word of all 1 bits, and then you just increase it by 1. So that causes an overflow, and then you get all zeros in EAX. So that's great. So that gives us a 0 in EAX. Okay. Yeah, so once we have that, then we write that 0 to the location in memory pointed at by EDX, which if we look up here, we had popped this address into EDX. Okay, so that terminates our string. Great. So our next step is we need to create an array containing a pointer to, let's see, all right, an array containing a pointer to the binsh string, which actually this address is not right. You should ignore that. Okay, so yeah, it's an address to the binsh string, and then that string is terminated with a null byte, of course, and then the array is also terminated with a null, a null D word, I guess, a 0, to indicate that there are no more elements in that array. Okay, so the place that I decided to stick this was just the start of the data segment, because I know that it's writable, and it shouldn't really matter what we overwrite in this, because we're just going to be, once we hit that return statement in the vulnerable function, we're just going to be executing our own opcodes that we've selected in our ROP chain. So let's see here. Okay, so yeah, so we can squash whatever we want, and it shouldn't matter too much. Okay, so we read in that data address, and then we read in the address to binsh, and we write it to that section in data. Okay, and then you'll see we do the same trick here. So, well, first off, we want to get the next address that we want to write to, which is just 4 bytes after the start of the data section here. Okay, because this address takes 4 bytes, then we want to write 4 null bytes here. Okay, so we do the same trick again to get zeros in EAX, and then we write those zeros to that location. Okay, so now we have this array sitting at the beginning of the data segment in memory, and now all we need to do is set up our pointers correctly. So we have this array, we have the string somewhere. Now we just put it all together. Okay, so we use this gadget with 3 different pop instructions, and it doesn't matter what we pop into EDX. I really just wanted to pop into ECX and EBX, so we can just put 4 bytes of junk here. All right, now then into ECX we wanted to load the pointer to the beginning of the data segment, so we do that here. And then EBX gets the pointer to the binsh string. Okay, and remember, here's that 01 again, because I wanted to avoid the null byte. All right, and then really I wanted, let's see here. So the value that's in EAX is 0 still from this. Okay, it hasn't changed. We haven't changed EAX anywhere. So now we go ahead and exchange that. So we want to put 0 into EDX, okay, because it doesn't really matter what's in EAX once we've swapped them, because we're just going to set it to 0 again here. Okay, and then you'll see all of these increases. So this is basically just to set EAX to 11, because you'll see in this line we actually jump to our interrupt excuse me, we return to our interrupt here, and we need EAX to be equal to 11, right? Okay, so if we look back through this, we've got EAX equal to 11. We have EDX equal to 0 because that was what was in EAX before and we exchanged them. And then we have ECX pointing to the array, which is at the beginning of data, and EBX pointing to the string with the binary in it that we want to execute. Okay, now if we go up and verify that, should be exactly what we needed here. Okay. All right, great. So that's how the exploit works. Now let's jump into our debugger and we'll kind of watch it do its magic. Okay, so I'm just going to set up the GDB environment a bit here. So I'm going to set the disassembly flavor to Intel just because at other parts of the demo I've been using the Intel dialect, and I prefer it to the AT&T for not really any good reason. Okay. Alright, so now let's go ahead and take a look at what the opcodes in our vulnerable function look like. Okay, now this call here to string copy, this is where we actually do the overflow, and we overwrite all the return addresses, and we write in our ROP chain. All right. So that means that if we stop right before this return instruction, we should be able to look at our stack and basically see our payload right there. Okay, so let's put a breakpoint there. Okay. All right, so let's see. So we've got a breakpoint set there. And now one other thing that I'm going to set up is a display expression here. And basically I want it to just show us the next two instructions that will be executed from EIP. Okay, so that just means anytime that it stops due to a breakpoint, it'll spit out the next two instructions to be executed. And that once we get into our ROP chain, once that starts executing, those next two instructions will usually be the next gadget that's run. All right. All right, so let's go ahead and run this. Okay, so now we can see that we're at that return statement. All right, you can see that we're at the return statement there, which means that we've already smashed our stack, right? So that, let's see here. So if we go ahead and look at what's on our stack, here we go. So we can see this is the address of the first gadget that we want to use, correct? Okay. So this is the start of our ROP chain here. And then also peppered throughout this, we can see these -1 or all 1-bit D words that we're using to set ECX to 0. Here we can see the A's that we have as our junk, our padding here. So that's where those come from. All right, and then all of these repeated over and over again that end in 2F. These are all addresses of the increment or increase gadget. Okay, and then we can see that it ends here with this one, which should be our interrupt gadget. Okay. All right, so what's going to happen here is we're at the return statement, and return is basically just pop EIP, right? So it's going to take this value and throw it into EIP. All right. So we'll go ahead and step. Okay. Now, one interesting thing here is that it shows us which functions we're in, and that will come into play a little bit later when I talk about some common issues with debugging ROP stuff. But okay, so yeah, so this is, we can see this is our first gadget, the pop EDX. Okay. And remember, this is we're trying to null terminate the string here, right? And now remember what I said about the start of the address? Okay, so the start of that buffer, this is that address. So if we look here, we have bin sh there, followed by a bunch of A's. All right. Now, so this is not yet null terminated. Okay, because we actually have not executed our first gadget yet. We're about to do that right here. Okay, so let's go through and we'll execute a few gadgets. Okay, and then let's see here. So we want to go until we execute this move statement. Okay, so here's the move gadget, and so we go ahead and execute that. Now let's look at that string again. All right, so we can see that it's null terminated because so this examine s means treat that memory like a string, so it just prints until it hits a null byte, and there's our null byte. All right, so that's great. So we've now null terminated the string. Okay. All right, so now we're in this set of gadgets here where we're building our array at the beginning of the data segment. So let's step through until we get to all of these pops here. All right, so so now we're at the pops, right? Because we have pop edx, pop ecx. It's the next two instructions, which means we've executed this whole chunk here. So that means that we should have an array built at the beginning of the data segment. And this is the address for the beginning of the data segment. So let's take a look at that and see what that looks like now. So I want to just print out, A stands for address. So I want to print out two addresses starting at this memory location here. Okay. Now the first address, if you remember, is the address of our string. Okay. So okay, so that's the address of our string. And then the next one is just zeros, right, to signify that that's the end of the array. Okay. So that means that this segment of gadgets has executed properly, and we've set this array up just like we need it to be. All right, so now the next step is, now that we have all of our data structures that we need, we have the string and we have that array of arguments, now we need to just make sure everything is in the correct register, and make sure that our EAX has the right value. Okay, so that's going to be the next chunk of this, chunk of gadgets. Okay. All right. So now we can see process is executing new program. Okay, so bin.sh was just executed. I guess on this system that happens to be a symlink to dash probably. Um, and so yeah, so we can confirm that that we are running a shell now. All right. Okay, so so that's great. All right. So cool. Now, what happened here at the end? That it went. I think I stepped one too many times because I wanted to pause right before this just to show you guys. Um, but yeah, so you can see here that EAX would have been set to 11, okay, because we start at -1 essentially, and we increment 12 times. And then, we have the address to the array popped into ECX. We have the address to the string popped into EBX. And then we have 0 in EDX. Okay? And if we go up again, and we see that that is exactly what we wanted for our execve call. All right. Now, if we scroll up, I wanted to talk about just a couple of issues with debugging ROP stuff, trying to get ROP exploits to work. So one interesting thing that I ran into when I was first setting this up was, so this interrupt that I'm using is actually inside of this setup TLS function, which is part of libc. And TLS is thread local storage. Now, execve is, as a system call, it's not supposed to return because you begin executing a new program. Now, what was happening before was I had some, my state wasn't getting set up properly, so I wasn't getting all of these values set up correctly. So when it tried to execve, it was failing, which would return from that system call with an error code. And now that int80 instruction is in here, which means that setup TLS is using, they're performing a system call of some kind. And it happens that the one that I'm using was to perform a system call to a thread local storage system call in Linux. And so when that returns as failing, the code that comes after it that shouldn't have executed at all begins executing, and that code contained like some error checks that said, "Oh, this system call failed. I guess we couldn't properly set up the thread local storage." So I was getting this error message back about couldn't set up thread local storage, and I was trying to figure out like why is it calling that system call? Why is it trying to do thread local storage? And I kept checking my EAX, like no, EAX is definitely 11. It should be doing execve. Why am I getting this error message? And it just finally occurred to me that, oh, it's because the system call is failing and it's just executing the code that's next, which happens to be, check to make sure that our system call was successful, and if it wasn't, then it must have been that we couldn't set up thread local storage. So yeah, so that was just that was an interesting time because I ended up wasting a lot of time trying to figure out why I was calling the wrong system call when what was actually happening was my execve call was just failing. Um, All right. Oops. Okay. So that's great. Um, let's see. So one other issue that I wanted to discuss really quickly was just that when you're executing binaries inside of the debugger, especially when you have ASLR enabled on your machine, by default the debugger will disable that ASLR. So that means that when you're using the debugger, you could have an exploit that works, and then you jump over, to your regular shell, and it doesn't behave like it was behaving in the debugger. So that's just something to keep in mind as you do this exploit development stuff. All right. So that's it for the demo. Thank you guys for watching, and I hope you enjoyed.